Too easy. Don't prove me wrong. Don't disappoint me. Okay, but something I want you to do tomorrow when you're writing your test is to actually just take a deep breath and to ask yourself what the question is asking you, right? Because there's so many times where people are just not answering the question, right? So please, take some time to read the question. This isn't a sprint. You got to be mindful about the way that you treat these things. Don't immediately start writing. I know that's your impulse. First, think, right? Really understand what the question is asking you, and then try to solve it. And then ask yourself, you know what the sniff test is? You ever took some milk out of the fridge, and you're like unsure if it was okay, you sort of give it a sniff? You need to do the same thing with your solutions. If you look at your solution and like, well, this seems like it's nonsense, right? Then you better like try and rework it. You should ask yourself, does the solution you provide, does it make sense? Right? You'd be surprised how many times people give answers which are just outright nonsensical in the problem statement. Anyways, today we have to talk more about derivatives of trig functions. So the motivating question here is, suppose I gave you an equation like this. What is the derivative of sine x? Anyone know? Yeah, so this should go to cos x. But at this point, we should be unsatisfied with these type of descriptions, right? Because now you should be asking, well, why? Right? I'm not allowed to just state this. So if we wanted to go about demonstrating this, what would be a good starting point? Yeah, we have to just use the definition. We have no other tools at our disposal. So we say d of dx of sine x is by definition this, which by definition uses the limit to get the value. Okay, so we get that. Any ideas for how we expand that? Well, what is, like, so we have to get rid of this h somehow. That's usually the strategy. But it's stuck in here, right? So there should be a rule that helps you expand signs over sums. Does anyone recall it? It's an important one. You should remember it. Okay, I'll write it. Where should I write it? Hidden board. All right, so here's something that you should remember. Sine a plus b, right? It's useful to know how sine works over a product. And it just goes like this. You say sine cos plus sine cos. And my mom is a huge fan of disco, so I remember it like this. Does anyone get that reference? Thank Christ. Okay, so it's ABBA. You spell ABBA in the middle, right? So sine cos, and then ABBA. You can do the other one too, but that's just bad. Like the point is that sine and cos stay fixed, and then you gotta do both. Anyway, so this is far more useful than the half angle and double angle formula. Because in fact, the half angle and double angle formula are very simple consequences of this formula. Okay, so given that I've now told you how to distribute these, how can I distribute this guy? I'll just do it for you. You get the limit as h goes to 0 of sine x cos h plus sine h cos x minus sine x. All of that is over h. If we continue, what do we get? Okay, so I'm going to do some factoring here. So look, I don't really care about anything in this equation that doesn't involve an h. Right? So even though this looks like it's something independent, sine x, it's independent of h. So this I want to isolate, and this I want to isolate. So let me just show you how I'm going to do that. I'm going to get the limit of h goes to 0. And then the first thing is I want to pull out a sine x. And what does sine x get multiplied by? Well, here's a sine x. So you get a cos h. And you also get a minus 1. That's over h. And then from that I have to, is it add or subtract? I have to add cos x and then sine h over h. Okay, so now what's the problem? I think I'm stuck. Unless one of you could tell me how to go from here. Well, let's just try evaluating things. What's sine at 0? 0. So this is 0 over 0. That's a problem. What's cos at 0? 1. 1 minus 1 is 0. This is also 0 over 0. That's also a problem. Okay, so I don't think... I'm going to tell you two things. The first thing I'm going to tell you is this. The limit of h goes to sine h over h is 0. That's a gift. We're going to use this. Now, today's lecture was supposed to be me explaining this. I don't like the proof. It's dirty. It's not elegant. You're not going to learn anything from it, so I'm going to skip it. But I need you to remember this. This is quite important. Yeah, this is quite important, especially when written properly. Okay, so this is the most important. Actually, what's consequent from this is that the limit of h goes to 0 of cos h minus 1 over h, and that's equal to 1, I believe. Yeah. Or did I reversed these? Oh, I'm teaching you wrong. It's hilarious. Sorry, this is a 1. This is a 0. Okay. So these are important. You got to remember this guy, especially. I'm going to put a star beside it. Right? There's going to be a very, very useful identity. In fact, I'm also going to put a star beside this. It's also very useful. Problem? Okay, so in any case, now that we're unstuck, how do I finish this? Well, what's this going to become? 0. What's this going to become? 1. Okay, so this is 0. That won't exist. So this is going to be equal to 0 plus, this is going to go to 1. So all we're going to be left with is cos x. So what have we found out? We found that sine x prime is cos x. Okay? So this is something that you all knew, but now you know why you know it. If you want to see the reason that sine h of h goes to 1, there's 100 explanations on it on the internet, and I think they'll do a much better job than I'll do, because they can really take their time. But you just have to remember that. That's the only thing, right? I'll rarely tell you to memorize something. This is one of these instances. Okay, does this, so what, like, let's, does this coincide with geometric interpretation? So let's take a look. Okay, so here's sine of x. I'm going to go through pi here. This should be 2 pi. Okay, so if this is the graph of sine of x, let's draw the graph of its derivative, right? We need another graph who's telling us what the slope is at any given point. So where are 2 points where we're absolutely sure what the slope is? Yes, sir?
Pi, 2 pi.
Well, okay, what's the slope?
Yeah, exactly. 0.
Is it that slope 0?
Oh, no.
No, but that's on the right track. So what about here?
0.
Okay, so here and here, the tangent line is definitely 0. Okay, so we know that the graph of the tangents, or the graph, okay, so I'm going to write a dot here. So the dot here means that at this point, this graph has tangent slope 0. We should also have, for the same reason, the graph of the derivative going through that. Okay, so let's ask ourselves some other things. If I start here, this is a quite steep slope that sort of gets smaller and smaller, but nonetheless positive until it hits 0. So it's a great slope that's still positive but decreasing. Then when I hit this 0 point, the slope is going to tilt like this. This is a negative slope. right? So it's going to be negative, and then even more and more and more steeply negative until it hits this point. So negative, 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 more negative until it hits that point. At this point, the slope is going to continue being negative, but getting weaker, right? We're going to get less and less steep until we hit this. And then after we hit here, you're going to get positive slope, which will do something like this. Okay. So what have I drawn? Cos. Right, so this is sine, and this is cos. Okay, so we've calculated something algebraically, and now I said, does this make sense? I'm doing the sniff test. So does it make sense that cos of x is the graph representing the values of the tangents of the slopes?
Yeah.
Yes, okay. So it shouldn't be any surprise then that the derivative of cos of x is equal to minus sine of x, because that's basically what this graph is saying. Right, so you could play the same trick, you just have to sort of flip the graph upside down. But otherwise, you can still prove this geometrically. It's like very similar to the sine x one. So I'm not going to repeat it. You can if you want. It's an exercise. It's not a bad thing to do. Okay, what's the next thing that we need? So we have a derivative for cos. We have a derivative for sine. We just got to keep going. What's the next natural thing that we should get a derivative for? Tan. Okay. So then what should the derivative of tan be? Anyone remember?
Was it secant?
I don't know. Suppose we forget. Okay, how would we go about doing this? Or finding it, right? Do we have to do a geometric thing, or do we have other techniques at our disposal now? Well, what did I teach you last class? Yes, sir. Absolutely, that's a great idea, right? Because the derivative of tan x is equal to the derivative of sine x over cos x. Is that true? Well, tan is just sine over cos. Can we continue?
We know the derivative as well.
Well, what rules did I teach you last week? Yes, sir. We used the quotient rule, right? So this is just going to be equal to sine x over cos x prime. Let's continue. Okay, so I'm just going to talk this out, right? I'm going to use the quotient rule. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared, yeah? Okay? What's the derivative of sine x? Cos x. So it's cos x times cos x is cos squared x. Okay, what's the derivative of cos x? Minus sine x. So minus sine x times minus sine x is positive sine squared x. We got all of that over cos squared x. Anyone see any simplifications? Pardon me? 1 over cos squared x, right? This is 1. Cos squared plus sine squared. So you get 1 over cos squared x, which I believe is the same thing as secant squared x. Either's fine. Let's just try and mull that over. How about those raptors?
You were there.
Who was there? I heard tickets now are like $12,000.
Yeah, for the finals. Imagine paying that much.
It's a status symbol now. All the rich people will show up.
Yeah, but imagine paying so much to watch it.
I did it for free on the internet. Okay, let's apply your knowledge. Here's an example. So thankfully, sort of most of the theoretical underpinnings that I needed to show you are more or less over. These classes should be going a little bit better now because I'm really just going to do like a billion questions and try to train you guys to do them as well. So how about this one? Y is equal to 5 e to the x plus cos x. Oh, sorry, cos x. What is y prime? Okay, so you look at these things and you say, okay, I need to take it, there's a sum, so I need to take derivatives of these things individually. So what's the derivative of this guy? It's the world's easiest thing to derive. Same thing. Well, at least until we get chain rule, but let's not talk. Okay, so this just goes to 5 e to the x. And then what does this go to? What's the derivative of cos x? Minus sine x. Okay. I would never ask you a question like this on a midterm because it's way too easy, right? I'd have to hide it behind another question somehow. Okay, let's try another one then. Well, what about y is sine x cos x? Yeah, product rule. Do you guys want to try or? You want to try? One lap. And do one lap. Come say hi to my YouTube subscribers. Oh, I think I have like 100. I'm basically a YouTuber. I hit that monetizing button. Make sure to smash that subscribe. Hit that bell. Hit that like. This lecture is brought to you by Matt Weldon. Back row. How you guys going? You get it? We the North bitches. I realize those uniforms are really smart though. They really should just change the name. Okay, so I'm going to do this. So I look at this, I see that there's a product, so I have to use the product rule for the derivative with respect to of y with respect to x. Derivative of the first times the second plus the first times the derivative of the second, which gives us what? So what does this derive to? Cos. So you got cos squared. What about this? So you got minus sine squared x. Okay, so far, nothing too difficult. Next one. Let us give this one a try. Y is equal to cos of x over 1 minus sine of x. You have till I wiped out my board. Ah! All right, obviously I want this, which is equal to this. So get used to both. So I'm trying to jump on the bandwagon and get a shirt. No. Double extra large. It was like, yesterday was like, double extra large, kids large. Fit into a youth. My absolute favorite thing are the Drake faces. It's good to know the Raptors finally have a mascot. Personally, I think he peaked in Degrassi. Okie dokie. So this should just be a pretty standard application of the quotient rule. So I'll just walk through it. So we have that y prime. So that's the derivative of the top. Cos of x prime times the bottom. Minus the top times the derivative of the bottom over the bottom squared. 1 minus sine of x squared. So what do we get here? I'm going to try to keep it on the same board. So this goes to what? Minus sine of x? So if this is minus sine of, I'm going to do two things at once. So this is going to go to minus sine of x, which means I get a sine squared x minus sine of x. Okay? And then, I haven't taught you chain rule yet. How are we supposed to do this one? Oh, no. I don't have to derive anything. That shouldn't be a 2. What am I doing? That's a prime. That should be this. Okay, so, what is the derivative of 1? What is the derivative of minus sine x? Minus cos x. So you're going to minus cos x, minus cos x. That's going to be positive cos squared x. All of that's going to be over 1 minus sine x squared. And what you see here, you get a 1. Sine squared and cos squared make 1. So you get 1 minus sine x in the numerator, which means we can cancel out one of these 1 minus sine x's in the denominator. So I get 1 over 1 minus sine x. And remember, if you're unhappy with the level of detail I'm giving in these examples, you should go home and fill in, like in your notes, leave a blank and fill it in. It's a good exercise. Okay, how about this one? Y equals secant x. What is the derivative of it? So what would you do?
Well, we can switch secant x there.
Yeah, okay, so let's switch out the secant x. That's a good idea. So can you do that? With what rule? Quotient rule. Okay, so I'm going to show you how to do it. It's a little bit different because we have a constant up here, but I'll show you. So we're going to have what? Okay, so it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Right? So like these derivatives aren't that hard as long as you're like just sort of going slowly and applying the rules. Okay, so let's finish this then. So what's 1 prime? 0. So who cares about that term? It's 0. I'll just write it in. What about this guy? Minus sine. There's a minus, so that goes to plus sine of x over cos squared of x. So I guess I have there's one tan like this is fine. Sine of x over cos squared of x is fine. Another way to write this would be 1 over cos of x tan x. And an even other way of writing it would be secant x tan x. So that's the whole point of these sort of inverse trig functions. It's so that we can like write everything on one line. I don't really care. I prefer this. Really, I prefer this. I like having everything in sine and cos. What else do I got for you today? Okay. Oh, yes. Okay. So I want you guys to work on this one for a few minutes. Same example. So y is equal to secant x. What is the second derivative of this function? Give it a try. I'll make a lap.
Wait, no, not that one.
Sine squared x. Oh, or the one. What was that sine? Squared x plus. So if you do minus integration, so 1 minus sine. You're talking about. No, so what you did, right? Negative sine. You minus sine instead of negative sine. Yeah, he's just expanding. He just expanded. He didn't do anything else. So that would be sine squared x minus sine x. And then the second part would be just squared x.
Can you please come to class next time with a printed out face of Trig? I would love that. Okay, so I'm just going to do it. Okay, so y prime, of course, is going to be the derivative of the derivative. So really this question is asking you to take the derivative of 1 over cos of x tan of x. Right? So let's continue that. So we're going to have, so I'm just going to use product rule, right? We have a product, so I'm going to use the product rule. So the first thing is the derivative of 1 over cos x times tan x plus 1 over cos x times the derivative of tan x. Okay, so what is this? Isn't that the thing that we just calculated? Oh, wow! Yeah, okay, so this is going to be secant squared, secant x tan x in here, right? Because we just calculated it. Don't do it again. And then tan x. And then you're going to get 1 over cos of x. And then what's this?
1 over secant.
Well, we worked it out, right? So I'm pretty sure this is 1 over cos squared. Okay? So what do we get? Maybe I shouldn't have written a secant here just to keep everything in the same. I'll just write 1 over cos of x. So you're going to get tan squared x over cos of x plus 1 over cos cubed of x. Or alternatively and equivalently and equally correct, secant x tan squared x plus secant cubed x. Everyone follow that? No? Like I'm getting some thumbs up, some no's. That was just a very straightforward application of the product rule and recycling old results. Okay, so stare at it, and if you still don't understand, we can walk through it. Okay, so now I'm going to give you a series of exercises to do. Pardon me? Oh, it's exclusively today.
Oh,
Yeah. No, it's out today. I think today's the first lecture that's outside of the testing. But like, don't get too comfortable because a couple weeks quiz, a couple weeks after that, another midterm.
Nice.
I wanted to do it on a weekly basis. I wanted to give you a midterm every 2 weeks. We didn't have the TA allocation for that.
I can get that here.
Yeah, I would have preferred it, right?
Worth less than
Okay, what is the limit of x goes to 0 of sine 3x over 2x? This is actually one of the core competencies from today. I'm supposed to show you how to do this, but I think you can figure it out. Okay, you got to get this to look like the rule that I gave you, with some modifications. But you definitely need to be able to do this, right? So if you can't figure it out, come and talk with me. Okay, so here's a good example of how I'm going to ask you to take a derivative by like asking you a different question. Where does cos of x have tangent slope equal to root 2? It's going to be in infinitely many places, right? Because it's a periodic function. The last exercise is going to be a little bit more complicated because it's a physics problem. Do you guys know how to work with springs? No? Okay. So I'm going to hang a weight from a spring. A weight is hung from a spring and is extended five units. Okay, so we're going to use this a lot. As a mathematician, I don't care about units. You just tell me what they are and I'll work with them. It could be meters, kilometers, nanometers. So as a mathematician, I just say units. It's just like a stand-in for eventually what they want. So it shouldn't make that. You can just regard this as meter if you want. It's extended 5 units from resting position. Okay, so here's sort of the picture. Okay, so here's positive 5 down here. Let's call this minus 5 up here, and let's call this 0. So we're going to have a spring, and you have a weight. And what I'm saying is that you put the weight on the spring, and the spring sort of extends to here, so which is what we're going to call the initial position, right? Oh, no, we're not going to call that the initial position. I'm going to then stretch. I'm going to stretch the spring, right, down 5 units and hold it here. It's going to gain some potential energy. We're going to call this time equals 0. Okay? Okay, so if this is time equals 0, we're going to be measuring displacement from this position. So I'm going to tell you that S of t, the displacement is equal to 5 cos of t. This is super unrealistic, physically speaking, because this would say that the spring is going up and down for forever. There's usually a dampening effect in that equation that we're not going to use. Right? Every time the spring goes up and down, it should be like stabilizing back to this position. But anyways, this is a really weird spring with an infinite amount of energy. Well, I don't think that's correct. It's a spring with perpetual motion, which is also impossible. But in any case, so this is the displacement. I want you to find out when, if any time, is the velocity equal to the acceleration? Oh, that's not even possible. That's a nonsense question. Calculate velocity and acceleration first. Not an S of t, time. When is the weight moving the fastest? And then when asides t equals 0 is acceleration equal to 0. Okay. When I ask you something like this, when does something occur? The answer is allowed to be never. In fact, the answer to this will be never. right? But don't treat this as a trick question. If I say, under what circumstances does this occur? You're allowed to say, there are no conditions for which this will occur. This is impossible. It will never happen. That's one way that you can answer a question when we ask if something exists. Is there any questions about that before we sort of just move into a more tutorial-like lecture? No? Yeah?
What did you write there? Does it say when assigned?
Yeah, when aside, well, obviously at t equals 0, nothing's moving.
What does assigned mean?
Not t equals 0.
Oh.
Like when,
So when?
like asides. Asides, is that not a word? Maybe this is a,
How do you spell it?
A-S-I-D-E-S.
Never heard of it. Literally never heard of it.
One other than
Define asides. All right.
Is it a word?
It is a word, but not the right one. How about besides?
Okay, that was.
Okay.
Listen, you try being raised by two immigrants from two different continents and see how well you speak English.